Hi all, greetings. Thank you for joining this session where we intend to talk about pod scaling abilities on power systems, and then hence we termed it as pod scaling ad infinitum. I'll briefly introduce myself. My name is Krishna Harsha Voora. I work as a software developer in cognitive systems of IBM India Software Development Labs. In this particular role, I help clients, specifically independent software vendors and business partners, in their journey to cloud and in their digital transformation. I play various roles wherein I help with porting of the required software stack onto IBM Power Systems, and then help with their validation and benchmarking exercises. I also focus on performance engineering aspects of ISV applications on Red Hat OpenShift container platform. With that said, I would like Mithun, my colleague, to introduce himself. Mithun, over to you.
Thanks, Harsha. I work with Harsha in the same team. So I work as a software developer, and it is kind of the same role. I also work as on different roles. I also work as a technical consultant, enabling ISVs port their packages onto IBM Power architecture, and also some of the performance work related to Power platform, and also some of the modernization stories around OpenShift container platform and in their cloud journey. So with that, I'll hand it over back to Harsha.
Thank you. Let's take a glimpse at today's agenda. We'll briefly touch base on IBM's and Red Hat's partnership. This has nothing to do with the acquisition, but how they have coexisted in the open source ecosystem. We'll spend some time on overview of Red Hat OpenShift container platform, and what are the best use cases that suits for OpenShift container platform. I'll also give an introduction towards the Power 9 model of service that can be leveraged for different workloads. We'll spend considerable amount of time on objective of the particular proof point study and how the workload is structured. And if time permits, we'll spend some time on a CAN demo, which is available in YouTube. IBM and Red Hat has coexisted in open source ecosystem for more than 20 years. And they have done a marvelous job, and they have come up with beautiful product portfolios which complement with each other as well. Speaking specifically from IBM Power Systems, Red Hat Enterprise Linux has been available on IBM Power Systems from quite a long time. That said, we also have had Red Hat's OpenStack available on IBM Power Systems. We also have now Red Hat's OpenShift container platform available on IBM Power Systems. I'll spend some time on the cloud workloads. If you take into consideration the operating systems in the cloud world, more than or near about 50% of them are Linux operating system. And Red Hat is indisputably the #1 service provider and Linux operating system distributor. That said, there is always an imminent threat to an enterprise workload that runs on a multi-cloud kind of a scenario, wherein presume your application makes use of a module, and then the vendor pulls back its support. How do we go about from there? This is a really typical scenario. It may or may not happen, but in order to cater to this solution and many other solutions, IBM and Red Hat have developed end-to-end solutions that addresses or helps unify public and private cloud investment and also mitigate vendor lock-in specific kind of issues. There are limitless applications with Red Hat OpenShift if only one understands its true capabilities and features that it brings onto the table. Boiling down to three major pillars, which we think plays crucial role in this era, are our application and infrastructure modernization story. As an analogy, think of an existing application which makes use of legacy software, and you want to cloudify or jump onto the train of modernization story. Red Hat's OpenShift provides you bundle of information or our application capabilities that, when leveraged, can help modernize your existing application. And once we leverage the existing utilities or tools, we can convert our applications, existing legacy applications, into microservice-based applications. When we switch to microservice-based application, your application availability or your application downtime goes to near about zero. Because it provides us the capability to do parallel upgrades and parallel rollouts. Speaking about building data-centric cloud applications, with data bursting at an exponential rate, the cloud internal organization have to think about the way they handle this information or how they handle the data that is at their disposal. New future clouds will also not only handle the data, but also will capture, process, and analyze the logs. Keeping this in mind, we should have an approach in such a way that we should bring the compute capabilities to the data as opposed to the traditional approach of bringing data to the compute capabilities. So this is typically possible by a hybrid multi-cloud kind of a structure, which Red Hat OpenShift already provides us. There's a lot of traction around artificial intelligence, specifically machine learning and deep learning. Red Hat OpenShift provides us a plugin which allows the model to run directly on GPU boxes, on your GPUs directly. And then we have a tailor-made server specifically designed to run your AI models much faster. That is AC922. I'll spend some time in the next slide. This is the Power 9, a couple of Power 9 architecture-based server models. If we categorize the entire slide into two vertical halves, on the left-hand side of the screen, we can see LC922 box. Its architecture is, and then the peripheral components are aligned in such a way that it helps process big data workload kind of workloads as pretty good. And then we have AC922. AC922 is a Lego building block of one of the supercomputers available in the world, that is Summit and Coral. AC922's planar surface is aligned in such a way that it allows you to pump enormous amount of data from your CPUs to GPUs pretty instantly, which allows us to spend considerable amount of time in training and testing your models. Moving on to the midsection of this particular slide, we have tailor-made servers, particularly for SAP HANA, H922 and H924, because they have a huge memory footprint requirement, and these two particular server models caters to the particular need. Similarly, we have S922, S914, and S924, which are scale-out systems with Power VM as a hypervisor, which primarily addresses OSDB kind of workloads, that is PostgreSQL, MongoDB, and others. Moving on to the last segment of this particular slide, we have Power Enterprise Systems, which is particularly targeted for enterprise kind of softwares, for example, DB2 and our Oracle. And then the beautiful thing is you can install Red Hat OpenShift across all of these server models that are available in front of you right now. For this particular proof point study, we have picked up a data intensive workload, which was very intentional because we wanted to stress the CPUs or the physical cores available both on power system as well as Skylake system, which is our competitive architecture in question. In order to match the data intensive nature of the workload, we have defined the objective of the workload as following, right? The main aspect of this particular objective was to derive a price performance at a per core advantage level. Sorry. So in order to do that, we have identified a workload, which was coming from geospatial workload from MongoDB's website, which was loosely based on mean stack. For audience who do not know what mean stack is, it is based on MongoDB, Express, JS, AngularJS, and Node.js. And then the nature of the workload was such that we could tamper it accordingly to make it CPU intensive workload. We have also defined service level agreements in order to define the metrics, which were acting as some rules in order to evaluate a workload. There were two in particular interest. One of them was if you trigger an API call, the response time should always be less than 999 milliseconds, less than or equal to 999 milliseconds. If we do not get any response, if any of the API responses takes more than 1 second or above, we categorize it as error news. What if we have more than many more such error news API responses, right? What we have defined was we could tolerate near about 1% of total API calls made to be error news. Anything more than 1% of total API calls which are error news, we categorize a particular workload or run as unfit. For example, if we have 100 such transactions and if we notice even one of the API calls are taking more than 999 milliseconds, we just disqualify that particular run. And then what we were also trying to do simultaneously were trying to pack as many containers as possible per host or on a per container basis. You can imagine container as an isolated environment where your developer is working without any performance degradations. So how many such developers can you accommodate through independent containers was the concept behind packing the many containers as on a host per as possible, right? Based on this particular SLAs and the metric systems that we have derived, we worked our way through the price and the performance ratio at a per core basis. This is really a busy chart. However, I'll try to keep it as minimalistic as possible. That said, the MongoDB geospatial dataset that we have picked up from MongoDB website contained a lot of collections within it. We were primarily interested in two collections, which is neighborhoods and restaurants primarily. In order to access this particular collection data, we have built in specifically API calls, which were tailor-made to hit this particular MongoDB datasets. You can imagine that you have picked up a phone and you're trying to query which is the nearest restaurant in your neighborhood, or which is the nearest neighborhoods next to your home. So what we have defined was, if a user picks up his phone and performs a transaction, it translates to 5 internal API calls, which basically are get my nearest 10 neighborhoods or get my immediate neighborhood, and then get the restaurants based in a donut kind of a shape, which was feed in via latitude and longitude geospatial ranges. and then restaurants in one particular range. In order to simulate the virtual users, what we have done is we have leveraged the meter automation tool that triggered or simulated the virtual users. For example, if 4 users triggered 10 such transactions or 10 such requests, it translates to 200 transactions. We categorized short and long runs. Short runs were near about less than 10 minutes, and long runs were near about 30 minutes. Long runs were crucially important to understand which component of the system was acting up good or getting stressed, or was it getting stressed? So during these long runs, we were collecting the performance data to analyze and tune accordingly. The software stack in question, when we have performed this particular proof point study at that point in time, is as follows. We have made use of version 3.11 of OpenShift Container Platform across both Power 9 and Skylake system. The choice of hypervisor on Power 9 was Power VM, and then the industry standard hypervisor KVM on Skylake system. We are trying to recreate the same workload on 4.5 version of OpenShift on Power as well as x86 systems as well. The operating system then compatible was RHEL 7.6 across both Power 9 and x86, and the kernel with which it was coming was 3.10. The container which was bundling both Node.js and MongoDB binaries was on top of CentOS, and then the kernel was almost the same because it basically shares the host kernel libraries or host kernel itself. And the MongoDB enterprise version was 4.0.2. It was consistent across Power 9 as well as x86. At that particular point in time, Node.js version was 8.14. So this is a typical topology diagram that we have considered and deployed in order to evaluate both Power 9 as well as Skylake system. So taking a look over here, we have two pure clusters. That's Power only cluster over here and Intel only cluster on the right side of the screen. The traffic to both the clusters were coming from same rack switch, and then the traffic was generated using the same workload generator, which is SA22LC powered box then. The Power VM resources were equally distributed across logical partition 1 and 2, that is 128 GB of RAM and 10 physical cores. Whereas on Intel, interestingly, we have given 18 physical cores to VM1 and VM2, and then RAM was 128 GB served accordingly. Let's take a look at the data flow. We have, in order to target the services exposed or the application services exposed, we have something called as OCP route, which allows us to access application services outside the cluster. OCP route, you can think of it as a unique URL. Yeah, you can think of it as a URL which is unique to both Power only cluster and Intel only cluster, right? So the rectangular blocks that you're seeing over here on the screen, they are physical representations. They are diagrammatical representation of the containers. They are hosting at the outset Node.js and MongoDB services. Similarly over here. So whenever we trigger a workload, we feed in the unique URL, and the data flow was getting targeted accordingly. So with this all, what does it mean when it comes to price performance ratio, right? So what we have taken into consideration is a IBM Power L922 box and then the Intel's Skylake box, which is 6148. they were almost the same. They almost have both same RAM, that is 256 GB, which is being shared across two VMs. And then at the outset, we were having 18 physical cores per VM and 10 physical cores per L power over here. If we do the math, what it means is we could we could showcase 3.2x greater container density per core, as in comparison to, and then with nearly 2.5 better price performance ratio. If it means on a container level, how costly were they? Assuming all of the math that's written over here, it's $666 per container in a way, and then this is nearly $1,750 on Intel. We have done a similar use case study on 19922 or the Mihawk systems, along with Skylake systems again. What we have seen was we could still maintain the lead of 2x greater container density deal on a per core basis, and then the price performance was near about 2.35 better than Intel system. But we have leveraged something called as QoS, which is quality of service. Basing on that, we could drive more transactions per second as in comparison to default QoS, which is, I think that's burstable, if I'm not wrong, or that's best of it. So we have 3 different quality of services classes or tiers, which is available at our disposal. And then this is something as a fundamental topic that comes for Kubernetes and has been consumed onto OpenShift as well. So you can think of a container and then how the resources can be defined to the particular container. The resources that can be defined and controlled are majorly CPU and RAM. And then if we both set the upper limit and the lower limit as equal, that's called as guaranteed quality of service. If we only set the request and optionally leave the limits field, you can think of request as the upper limit and limits as the lower limit. If you set only the upper limit and leave out the lower limit, we get something called as burstable quality of service. If we do not define any, that gets by default classified as best efforts. So when we did that particular test, I'm switching back to the previous slide, what happened was we could drive more transactions per second. But keeping in view the agenda of this particular use case study was to pack as many containers as possible. In this particular result, what we have also did was driven a great deal of TPS. I think we are short on time for the YouTube video. Mithun, is that right?
We have 5 more minutes. I think we can go to Q&A.
All right. Yeah, I think I'll just take a pause if in case you have any question.
We have one question. We have 2 questions actually. One, is there a plan to upgrade it to OpenShift 4.5 from Frederick to see if it makes any difference? Harsha, do you want to answer?
Yeah. So I think OpenShift 4.5 is in fact OpenShift 4.x is really different in the architecture, the way it brings onto the table as in comparison to OpenShift version 3. That said, we do assume that there will be some performance benefit if you run it on power systems, but it will be too early to make that statement. we would want to do some tests which are right now under progress, and then we'll see how it comes along. I think it will definitely make a difference, but we need to understand how or what's a driving factor. I'm not sure.
Okay,
If
we have one more question from Vipin. In performance comparison, can you explain if Skylake 20 core is enabled with SMT? Is first part of the question. Second part is if IC922 is enabled with SMT4. And third part is the 10G internet interconnect is per NUMA or 1 into 10G on NUMA. And Vipin has asked if you can share some insight on KVM running on Skylake. Reason there are only 4 threads which are mentioned, 40 threads which are mentioned in the slide.
That's correct. So I'll just switch back to the particular comparison. So let me answer your question. That is, Skylake 20 cores is enabled with SMT. SMT is a concept associated with power systems only. The equivalent terminology for that will be Hyper-V. And then, yes, it was enabled on the Intel systems. And then that's how we could drive 40 virtual threads, and then if IC922, yes, IC922 was enabled with only SMT4. That's correct. The 10 gig interconnect is per NUMA or 1 into. I think I need to get back to you on question C. Vipin, I think I'll reach out to you. I'll try to get the details and find out to you, and then get back to you on this. Can you share insight to KVM running on Skylake? I do not quite follow this question. Can you elaborate more on this? Okay, so all of the cores are associated to KVM. Yeah. Right. So moving on to the second question, which Vipin has just posted, right? That is, okay, so we have 20 physical cores. If we enable Hyper-V, then we will get 40 vCPUs, or that's how it will be. 40 hardware threads. You can think of it in that way. Exactly. We have done the CPU pinning of the questions as well. Yeah.
Yeah, Vipin, I have allowed unmuted. Yeah, go ahead.
Yeah. Okay. So I was just a couple of things which was not clear to me was like the Skylake 6148 Xeon that you mentioned, right?
Mm-hmm.
Each is having 20 cores, and since there are two NUMA, there would be 40 cores, and if hyper-threading or SMT is enabled, wouldn't that make it 80 threads available to it?
So I was talking about, that's a very good point. I was talking at the per socket level. Exactly.
Oh, okay.
Yeah.
Okay.
So this is a 2-socket box. So each socket having 20 cores. Yes. In total, we have 40 physical cores. And exactly, yes. This is, we have 80 80 hardware threads that we can leverage. Yes.
Absolutely. And when I think about Power IC922, it has 20 plus 20 with SMT4 enabled makes it 40 into 4, 160 threads. That was
That's
my
right.
understanding. And you have used Core 0, if I'm not wrong, to run the Linux on the host. That is why one thread per one container. So that is why you have 159 on PowerPC and 79 on Xeon. That is what I am assuming. Is that the right understanding?
That's one way of doing the math. Yes, but to answer your question, pretty short and clean, right?
Yeah.
So we could, the one thread, that's exactly true, one container per thread. And the one thread
Correct.
that we had to leave out was because we had to ensure OpenShift container platform was also running.
Absolutely. I agree. Yeah.
Yeah. So basically, it was OpenShift container platform as well as KVM and operating system running on one thread.
Absolutely. So in Skylake, the KVM and OpenShift runs on, let's say, that core 0. Perfect. But in IBM with IC92, I thought it was a hardware KVM. So the OpenShift only need to be run on core 0 with some management activity from OS is what I was trying to understand. So you do have power savings and you do have the core impact savings with that. That is what I was trying to compare. But thank you. I think I got a picture.
Thank you very much.
Yep.
Yeah.
Yep. Thank you.
Yeah. And then, guys, if in case you have any more questions, please feel free to post them on our Slack channel.